Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore the architecture that reshaped modern AI, the transformer, how it works, why it replaced recurrent models, and why it became the foundation of today's large language models.
Yeah, and it really is a seismic shift. It's hard to overstate it. If you want to understand the DNA of modern AI, everything from GPT to these incredible image generators, you have to start here. The transformer is what defines this entire era.
Okay, so let's set the stage a bit. What did the world look like before, say, 2017? If you were working with sequences like text or audio, you were probably using neural networks, right? RNNs.
Exactly. RNNs and their, let's say, more powerful cousins, LSTM, long short-term memory models. They were the undisputed champions for any kind of sequential data. But they had this one massive built-in flaw. They had to process things sequentially.
One at a time, in order.
One at a time, in a strict order. Think of it like you're reading a really long scroll. You can't just jump to the middle. You have to start at the very beginning and read every single word in order to get to the end.
That just sounds slow by definition. I mean, that must have been a huge bottleneck for training, but it also feels like it would cause problems for understanding the big picture.
You've just nailed the two fundamental problems right there. Let's start with the context one, which engineers called the short-term dependency problem. Because the model is processing word by word, it keeps a sort of summary, a hidden state that it passes from step 1 to step 2, then from 2 to 3, and so on.
So it's like you're summarizing a book, but you only get to use the summary of the last chapter to write the summary for the next one.
That's a perfect analogy. By the time you get to the 100th word in a sentence, the information from the first few words has been processed and compressed and filtered 90-something times. That original crucial signal, like, the subject of the sentence, it just gets weaker and weaker. It fades.
It gets lost.
It gets lost. And this made it incredibly difficult for RNNs to handle long sentences and really grasp the context. The model would literally forget the beginning of the sentence by the time it got to the end.
So if I had a long, complex sentence like, the delivery truck, which was carrying fragile antiques and got stuck in a freak snowstorm, finally arrived, the model might lose the connection between truck and arrived.
Precisely. That long-range dependency was a constant, painful problem. But the second issue was, from an engineering perspective, maybe even bigger, and that was the training speed.
Because you can't process word 5 until you're done with word 4.
You got it. And that means you can't really take advantage of modern computers. GPUs, graphics processing units, are amazing at doing thousands of calculations at the same time. They're parallel processors.
But the RNNs force them into a single file line.
Exactly. It completely bottlenecked the training. As datasets got bigger and bigger, trying to train a really large, complex RNN became just computationally impossible for most people. The architecture itself was holding back progress.
Okay, that sets the stage perfectly for the big moment. The transformer arrives and basically says, we don't need to do things in order anymore. It just throws out recurrence for a totally new idea.
Attention. That's the whole idea behind the famous attention is all you need paper. The solution wasn't to build a slightly better RNN. It was to get rid of recurrence entirely and make attention the main computational engine.
So instead of looking at one word after another,
it looks at all the words at the same time.
And the immediate benefit of that has to be a huge jump in speed and efficiency. You're breaking that sequential chain.
Absolutely. It wasn't just a small improvement, it was a complete game changer, an enabler. Because the calculation for any given word no longer depends on the result of the word before it. You can just throw the entire sentence onto a GPU and figure out all the relationships simultaneously.
So now we can finally use these massive computer farms the way they were designed.
Correct. And that massive speed up meant we could train faster, but more importantly, we could train bigger models on more data. It just blew past that old slow bottleneck of the RNNs.
So conceptually, how does attention work differently to build context? If it's looking at everything at once, how does it know which words are important to which other words?
That's the elegance of it. Recurrence builds context step by step, locally. Attention builds it globally, all at once. It lets the model look at every single pair of words in a sentence and calculate a relevant score between them. It actively learns where to put its focus, no matter how far apart the words are.
Ah, so it doesn't need information to be passed down a long chain and get diluted.
It just looks directly where it needs to. It proactively finds the most important connections.
It's like being able to just glance at a whole page and instantly see the two sentences that are most related to each other instead of having to read from the top down.
That's a great way to think about it. It gives the model a holistic view of the meaning right from the start, which is how it just naturally solves that long-range dependency problem that plagued the RNNs.
Okay, let's get under the hood of the original design. It was built for machine translation, right? Turning a sentence in one language into another.
Yes, a sequence-to-sequence task. The original architecture had two main components, or stacks, the encoder and the decoder. You'd usually have a stack of 6 encoders and a stack of 6 decoders.
Let's start with the encoder. What's its job?
The encoder is the reader. Its only job is to understand the input sentence as deeply as possible. It takes the original sentence, say in German, and it chews on it, building up a rich, contextualized mathematical representation of what that sentence means.
So it's not generating anything, it's just thinking, comprehending.
Exactly. It's creating this set of vectors that captures all the nuances and relationships in the input. Once it's done, it hands that package of understanding over to the decoder.
And the decoder is the writer.
The decoder is the writer. Its job is to generate the output sentence in English, one word at a time. It works autoregressively, which is a fancy way of saying it generates the next word based on the words it's already generated.
Okay, so the encoder is the expert reader, the decoder is the careful writer. How do they make sure the writer is staying true to what the reader understood? How do they communicate?
That's a great question. They communicate through a special form of attention called cross-attention. At every step, as the decoder is trying to decide on the next word to write, it doesn't just look at its own work. It looks back at the encoder's final understanding of the entire input sentence.
So it's constantly checking its work against the source material.
Constantly. It's effectively asking, okay, given the English words I've written so far, which of the German words from the original sentence are most important for me to focus on right now to generate the next word?
Wow. So even when it's writing the very last word of a long translated sentence, it can still directly refer back to the very first word of the original.
That's exactly right. And that connection ensures the translation is accurate and faithful to the full context of the original input. Is what made this structure so powerful for translation.
This brings us right to the core mechanism then. Self-attention. This is what's happening inside the encoder, for example, to build that initial understanding. How does this query, key, and value system work in an intuitive way?
Okay, so imagine every word that goes into the transformer gets 3 different hats or 3 identities, a query, a key, and a value. They're all just vectors, but they have different jobs.
3 hats. Okay. Let's take an ambiguous word like bank. It could be a river bank or a financial bank.
Perfect example. So we're focusing on the word bank. Its query vector, its Q, is like its search request. It's the word asking the rest of the sentence, hey, what information do you all have that can help me figure out what I mean here?
So it's the active seeker of information. What about the key?
The key vector, or K, is like an advertisement. Every other word in the sentence holds up its key and says, this is the kind of information I have to offer. The word river has a key, the word money has a key, and so on.
I see. So the model takes the query from our word bank and compares it against the keys of every other word in the sentence.
Exactly. That comparison gives you an attention score. It's a measure of relevance. The query for bank will match very strongly with the key for river, so that score will be high. It might match very weakly with the key for, say, car, so that score will be low.
Okay, so we have relevance scores. And that's where the third hat, the value, comes in.
The value vector, V, contains the actual substance, the real meaning of that word. So once the model has all those attention scores, it uses them as weights. It will heavily weight the value vector of river and barely weight the value vector of car. It then blends all those weighted values together.
So the final updated representation of bank is now a mix of its original meaning plus a big dose of the meaning of river and almost none of the meaning of car.
Precisely. And just like that, the ambiguity is gone. Bank now understands that it means riverbank because it drew context from the entire sentence at once. That's the mechanism that lets it bypass that whole sequential memory problem.
It is a really elegant solution, but it feels like if you only do that calculation once, the model might get fixated on just one type of relationship, maybe. Like it might only see the subject-verb connection but miss something more subtle.
That is a very sharp observation, and it's exactly the reason the designers created multi-head attention. A single attention calculation, or a single head, can often become a specialist in just one kind of linguistic relationship. And language is way too complex for that.
So the solution is just run the whole attention process multiple times in parallel.
Pretty much, yeah. You run the whole QKV calculation, say 8 or 12 times in parallel. Each one is a separate head. And here's the key part. Each head has its own independent set of learnable weights, so they all learn to look for different things.
So you basically have a panel of 8 different experts looking at the same sentence at the same time, each with their own specialty.
That's a great way to put it. You're trying to extract the maximum amount of information about the dependencies in the sentence. So for example, let's take a sentence like, the cat, which was hiding under the old wooden porch, finally pounced on the toy.
Okay.
Head 1 might be a grammar specialist. It sees cat is the subject and pounced is the verb, and it links them together, ignoring all the descriptive stuff in between. Head 2 might be a pronoun specialist, and its job is to figure out that which refers back to the cat.
And maybe a third head is looking at semantic concepts, linking hiding, porch, and pounced to understand the general action of the scene.
Absolutely. And maybe another head is looking for longer range connections. By splitting the work across multiple specialist heads, the model gets a much richer, more layered understanding of the data's complexity than any single head could ever provide on its own.
That makes the representation incredibly dense and powerful. But this brings us back to a problem we mentioned earlier. We got all this power by processing in parallel, which means the model is, by default, order agnostic.
Yes, the big flaw.
If I give it man bites dog versus dog bites man, the attention scores between the words would be identical because it only cares about the relationships, not their position in the line.
And that's a fatal flaw for language. Word order is meaning. The transformer absolutely has to know the order of the words, otherwise its output is meaningless.
So how do you put order back into this orderless system without, breaking the parallelism that makes it so fast?
The solution is really quite clever. It's called positional encoding. Before any of the words even enter the first layer of the transformer, we inject information about their position. First, the word is converted into its meaning vector, its embedding. Then, we literally add another vector to it, a vector that uniquely identifies its position in the sequence.
So the word dog in position 1 gets a vector that essentially says, I am number 1. And if it's in position 5, it gets a different vector that says, I am number 5.
That's the idea. The original paper used a really elegant method with sine and cosine functions to generate these positional vectors. It creates a unique wave-like pattern for each position that the model can easily learn to interpret.
Why something so complex, like sine waves, instead of just counting? 1, 2, 3.
It's because the sinusoidal functions have properties that make it easy for the model to understand relative positions. It can learn, for example, what it means for 2 words to be 4 steps apart, no matter where they are in the sentence. It's a very robust and scalable way to blend that crucial position information right in with the word's meaning.
That's a brilliant piece of engineering. Okay, so we've got the word meaning, we've tagged it with its position, and we've run it through multi-head attention to gather all this rich context. What happens next in a single layer?
After the information has been gathered and mixed by the multi-head attention block, it goes through one more crucial step within that layer. It's called the pointwise feed-forward network, or FFN.
And what's the FFN's role? Is it doing more attention?
No, the attention part is done. The FFN is for processing and refinement. You can think of it as a small internal neural network. After attention has gathered all this context from across the sentence and packed it into each word's vector, the FFN takes that newly contextualized vector and processes it further.
A refinement shop. I like that.
It's a chance for the model to sort of
Yeah.
think about the new information it just gathered. It applies a nonlinear transformation, which helps the model learn more complex patterns from the contextualized data before passing it up to the next layer in the stack.
So it's a way to add more computational depth and representational power without just adding more and more attention heads.
Exactly. It's a crucial step for digesting the information that attention provides.
Now, modern models are incredibly deep. They stack dozens of these layers. And in deep learning, that's historically been a recipe for disaster. Information gets lost or the training becomes unstable. How do transformers handle being so deep?
This is where 2 of the most important but least glamorous engineering tricks come into play: residual connections and layer normalization.
Usually just called add and norm.
Right. Let's start with the add part, the residual connections. It's a very simple idea. You take the input that's about to go into a block, like the attention block, and you create a little shortcut, a bypass lane for it, After the block has done its complex processing, you just add the original untouched input right back to the output.
And why is that so important?
It's an information highway. It guarantees that no matter how many complex transformations the data goes through, the original signal never gets lost. It prevents the problem of gradients vanishing in very deep networks, ensuring the model can always learn effectively, even with 100 layers.
So the core message is always preserved because it has a direct path. And then you have the norm part, layer normalization.
Yes, normalization is all about stability. During training, the numbers inside the network can swing wildly, getting very large or very small, which can make the learning process erratic or completely break it.
That's the classic vanishing or exploding gradient problem.
The very same. Layer normalization just recalibrates the numbers at each step, keeping them in a nice, stable, predictable range. These two things together, residual connections and layer normalization, are the engineering backbone that makes it possible to train these massive, deep transformer models we see today.
It's fascinating. The big idea is attention, but the thing that actually made it practical and scalable is this really smart, careful engineering.
It's the infrastructure that lets the big idea shine.
Which brings us right back to parallelism and scaling. The fact that attention could run in parallel is what let us escape the sequential trap.
And that one shift unlocked the entire modern era of AI.
Right.
Because transformers could use GPUs efficiently, researchers could just make everything bigger, more layers, bigger models, and train them on vastly more data than was ever possible with RNNs.
This is where those scaling laws started to appear, isn't it? The idea that you could pretty reliably predict that if you threw more data and more compute at a transformer, it would just get better.
Precisely. Researchers found this predictable relationship. More data, more parameters, more compute time directly translated into better performance. This is what led to the explosion in model size, from millions of parameters in the early models to the hundreds of billions or even trillions we see now.
And that predictable scaling changed the whole field.
It did. It turned cutting-edge AI research into a game of scale and infrastructure. But the results were undeniable. These huge models with their massive capacities started demonstrating abilities that we had never seen before.
Now, the original transformer had that full encoder-decoder architecture, which was great for translation. But since then, the community has kind of split it into three main flavors. Let's start with the first type, encoder-only models.
Right, so models like BERT, they just take the encoder stack and that's it. And if you remember the encoder's job, it's all about understanding. It looks at the entire sentence at once, from left to right and right to left, to build a deep bidirectional understanding of the context.
So it's perfect for analysis tasks. If I want to classify a document's sentiment or pull out all the names of people, an encoder-only model is the tool for the job.
Absolutely. Text classification, named entity recognition, question answering where you're analyzing a piece of text. For anything that requires a deep understanding of existing text, BERT-style models are king.
Then on the complete opposite side, you have the creative ones, the decoder-only models like the GPT family.
Exactly. These models just use the decoder stack. Their whole job is generation. They stick to that autoregressive process of generating text one word at a time based on the words that came before.
But how do they stop themselves from cheating and looking ahead at the words they're supposed to be predicting?
They use a clever trick called masking. When the self-attention mechanism is running inside the decoder, it's literally forbidden from looking at any words that come after the current position it's working on. This forces it to be purely predictive, only using past information to guess the future.
Which makes them perfect for generative tasks. Writing stories, chatbots, anything that involves creating new text from a prompt.
Precisely. They are the foundation of modern generative AI. And then, of course, you still have the full encoder-decoder models like T5 that use the original complete architecture.
And their sweet spot is still that sequence-to-sequence work.
Yep. They shine when you need to map one distinct sequence to another distinct sequence. Translation is still the classic case, but also things like summarization, where you take a long article as input and generate a short paragraph as output.
What's maybe most incredible about all this is that an architecture designed to solve a language problem turned out to be so much more versatile. It's become this general-purpose reasoning engine.
It really has. The core idea, using attention to find relationships between elements in a sequence, is totally domain agnostic. You can turn almost anything into a sequence.
The biggest leap was probably into computer vision with the vision transformer, or VIT. How on earth do you turn a picture into a sequence of words?
You don't. You turn it into a sequence of patches. You literally take the image and chop it up into a grid of little squares, say 16 by 16 pixels each. You flatten each patch into a vector, and then you just treat that list of patches as if it were a sentence.
So instead of a sequence of 20 words, you have a sequence of, say, 256 image patches.
Exactly. You add positional encodings to them so the model knows where each patch was in the original grid, and you feed it into a standard transformer encoder. The self-attention mechanism that goes to work, figuring out the relationships between every patch and every other patch in the image.
That's such a different way of thinking compared to the old convolutional neural networks, the CNNs, which were all about finding local features like edges and textures.
And that's the key difference. The VIT is all about global context from day one. It can see the relationship between a patch showing an ear on the left side of the image and a patch showing a tail on the right side, and understand they belong to the same animal. It gets that holistic view that CNNs had to build up slowly over many layers.
And the performance has been amazing. VITs have basically taken over many of the top spots in computer vision.
They have. And now we're seeing the best of both worlds with hybrid models. Things like conformer models, which use a bit of CNN-style processing to capture those fine-grained local details and then feed those features into a transformer to figure out the global long-range context. It's a very powerful combination.
And this has gone way beyond just images. It's deep into signal processing now, too. Audio, medical data.
Oh, absolutely. In audio, models like Whisper for speech recognition are transformer-based. They can look at a long chunk of audio and use attention to figure out context, which is perfect for understanding noisy or ambiguous speech.
And you see it in really critical infrastructure systems now where the old RNNs used to fail because of their short memory.
Yes, think about cloud computing. Forecasting resource demand means looking at usage patterns over months or even years. An RNN would forget what happened last Christmas by the time it saw data from January.
But the transformer can directly link that Christmas spike to what's happening now.
It can. We're seeing transformers used to optimize job scheduling in data centers and manage wireless networks by analyzing long-term historical data. It's perfect for finding those long-range seasonal patterns.
And it's the same story with medical signals, I imagine. EEGs, ECGs. Those are very long, complex sequences.
Exactly right. For something like classifying an ECG for a heart arrhythmia, you're looking at long, complex wave patterns. Hybrid models are common here too, using something to find the local heartbeat pattern, and then a transformer to understand the sequence of those patterns over a long period of time. They're often way more efficient than older methods.
It really feels like the transformer has become the default tool for any problem, where long-range context is the key to solving it.
That's its legacy. It's so fundamental that it's even being explored in fields like molecular chemistry and, believe it or not, in hybrid quantum classical computing models.
Wait, how does a quantum computer get involved with the transformer?
It's very experimental. But the most computationally heavy part of attention is that comparison between all the queries and all the keys. Some researchers are exploring if they can offload that massive comparison task to a quantum circuit, hoping it could do it even faster or more efficiently.
So the core idea of attention remains, but the engine doing the heavy lifting could one day be quantum. That's incredible.
It just shows how foundational the architecture is. It's the bedrock that all these modern foundation models are built on.
Looking back, it's so clear. The transformer solved the scaling problem, it solved the long-term memory problem, and in doing so, it unlocked all these emergent abilities we see in today's most advanced AI.
It turned sequence modeling from this very constrained one-at-a-time problem into an expansive, parallel, and scalable one. That's why it's the blueprint for state-of-the-art AI everywhere you look.
You know, there's one final thought I have on this, and it's a bit more philosophical. We've built this amazing system based on attention, but some of the research I've seen suggests that the attention maps these models create, the way they actually decide what's important, sometimes look less like human attention patterns than the older, less powerful models like LSTMs did.
That's a fascinating and counterintuitive finding, isn't it? We built a system that performs far better than anything before it. But the way it thinks or pays attention might actually be less human-like.
It raises a really interesting question. If the path to maximum performance involves creating an intelligence that processes information in a fundamentally non-human, maybe even alien way, what does that imply? Is mimicking human cognition the best path forward, or is it actually a limitation we need to overcome? It's something to mull over.
It really is. The data seems to suggest that the most effective path for the machine might not be the one that mirrors our own minds.
Thanks for exploring the depths of this architecture with me.
It was a pleasure.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.